Welcome back. We've been talking about Newton's method. We've talked about the motivation. We've talked about the detailed algorithm, phase 1 and phase 2. And we've also talked about how phase 2, once we get close to the optimal solution, we start using undamped Newton's method, and the guarantee of the result of the theorem is that we have quadratic convergence. And we discussed exactly how powerful and how fast that is in the previous lecture. Let's now give the proof for the quadratic convergence phase. In other words, the proof of phase 2. So we're going to show the following. First, the assumptions. Again, the setting is the same setting we've been in throughout this entire course. We're minimizing a convex function. However, in addition, we're assuming that f satisfies the following. It is little m strongly convex. It is, of course, twice differentiable, so that the Hessian can be computed. And note that strongly convexity plus existence of a Hessian is equivalent to saying that the Hessian of f has the smallest eigenvalue that is always greater than or equal to m over 2. And in notation, I can write it like this, which is exactly the same as writing that the matrix that's equal to the Hessian minus m over 2 times I is positive semi-definite. So strong convexity, and I should, just to make it explicit, plus twice differentiable is equivalent to this condition. We're also going to assume that the Hessian is Lipschitz. So we've talked about the function f being Lipschitz. We've talked about the gradient being Lipschitz. That's a definition of what we call smoothness in convex optimization. But for Newton's method, we also require that we have a Lipschitz constant on the Hessian. So Hessian is L Lipschitz. And writing out the condition again of what this means, this is saying that the Hessian evaluated at x compared to the Hessian evaluated at y, the operator norm, sometimes denoted by OP or sometimes denoted by 2 for the 2 norm of the matrix. This is the largest singular value of this matrix, is bounded above by my Lipschitz constant L times x minus y, the 2 norm. And we're also going to assume that our initial point is close to the optimal solution. So this is what it means to be in phase 2. And remember that this is something we can detect because of strong convexity. We discussed this at length in the previous lecture. We can detect that we're close just by looking and seeing whether the gradient is small enough. So we're also going to assume that x0 minus x star in the 2 norm is bounded above by little m, the strong convexity parameter, divided by twice capital L, the Lipschitz parameter of the Hessian. And again, the only reason I mentioned this, that strong convexity allows us to check, is that otherwise this wouldn't be a very useful condition because we don't know what x star is, so we can't estimate x0 minus x star. Possibly we can upper bound it by something very big, but we can't reliably tell just by itself when it's very small, unless we have strong convexity, in which case just by certifying that the gradient is small, we're sure that we're also close. Okay, so what are we going to use? The main element of the proof is going to rely, just as we've seen in other proofs, this is generally a common tool in convex optimization and convex analysis, we're going to use the fundamental theorem of calculus. So let's remember this one more time. Again, we've used this before in these lectures. So the fundamental theorem of calculus basically says that integrals and derivatives are inverses of each other. Or in other words, if I take the integral of the derivative of a function, that's equal to the function evaluated at the endpoints. So specifically, the integral from 0 to 1 of d dt of a function capital F of t, I'm just using capital F so we don't necessarily associate it with the function that we're optimizing here. It's an arbitrary function, is equal to f of 1 minus f of 0, the function evaluated at the endpoints. So let's see how we're going to use it in this case. So the fundamental theorem of calculus tells us that the gradient of f evaluated at x plus d minus the gradient of f evaluated at x. So you can see that this looks a lot like a function evaluated at its endpoints. So I would like to write this as the integral of a derivative. That's the spirit of how we're going to try to use this. So this is the integral of the derivative, and I know what goes in here. What goes in here is the function where if I evaluate it at 1, I get gradient of f at x plus d, and if I evaluate it at 0, I get gradient of f of x. That way, a direct application of the fundamental theorem of calculus will give me this relationship. So that's just the gradient of f at x plus t times d and dt. And just looking again at this, fundamental theorem of calculus tells me that what's on the right is what's inside the derivative evaluated at at 1. That's gradient of f of x plus 1 times d minus that thing evaluated at 0, which is gradient of f of x. So indeed, I have this equality. And you can see that what this allows me to do, the way that I'm using the fundamental theorem of calculus, is it allows me to relate gradients with one more derivative, Hessian. We've also used this to allow us to relate the function with the integral of its gradient. We saw that this technique was useful in a previous lecture in that context. So generically, it just allows me to add one more derivative here. And I want to do that because the key new property that we have, the key new assumption that we're using is that the Hessian is Lipschitz. So I have to come up with a Hessian somewhere in here. And this is what's going to allow me to introduce a Hessian. Okay, so now let's write down what this derivative is inside. And this is, I just need to use a chain rule, otherwise it's quite simple. So the derivative of the gradient is the Hessian, there it is, x plus td. And then I just need to multiply by the derivative of the inside. Note that this is a function of t. I'm taking the derivative with respect to t, so it's just a single variable function. And so what comes out, the derivative of the inside with respect to t, is just the vector d. So I've got a matrix times a vector. So on the right, I have the integral of a bunch of vectors, which makes sense. We should be relieved because on the left, we have vectors. Okay, so now let's see how we're going to apply this. We will apply this relationship by using x. I'm going to plug in x star for x. And for d, I'm going to plug in xk minus x star. So I'm going to do this on the next page, but you can see what we're going to get. We're going to get the gradient of f evaluated at not x plus d, but x star plus xk minus x star. So let's plug this in and we'll see how it looks. So again, using the expression on the previous slide with x equals x star and d equal to xk minus x star, exactly what we had written gives us that the gradient of f of xk minus the gradient of f of x star. And what is that? Well, x star is the optimal solution. This is an unconstrained optimization problem, so we know that this is 0. Is equal to the integral from 0 to 1 of the Hessian of f evaluated at, again, I'm plugging in x equals x star and d equals xk minus x star in my expression inside the integral that I had from the previous slide. And I'll find that this is equal to the integral of the Hessian evaluated at x star plus t times xk minus x star times xk minus x star dt. So just trace back to make sure that you understand exactly what this says, where this came from. Okay, so now I have an expression for the gradient that looks like an integral of the Hessian. And now I'm going to write out what xk plus 1 is. We know what xk plus 1 is. It's just it's a Newton step with eta equals to 1 because we're in phase 2, which is undamped. So xk plus 1 is equal to xk minus the Hessian at xk inverse times the gradient of f evaluated at xk. So that means that xk plus 1 minus x star is just equal to this right-hand side minus x star. So I'm going to write it like that. Xk minus x star minus the Hessian inverse. Okay, now I could just write the gradient, but we have a different expression for the gradient that we just derived. So that's what I'm going to use. I'm going to plug in from up top of the top of the slide our expression for the gradient, the integral from 0 to 1 of the Hessian evaluated at x star plus t times xk minus x star times the vector xk minus x star dt. Okay, just plugging that in directly. Okay, so let's see how we can group this together further. So note that the xk minus x star, I can just write this as the gradient, the Hessian at xk inverse times the Hessian times xk minus x star. This is just, I've just multiplied by another name for 1 here. And another way to write xk minus x star is the integral from 0 to 1 of xk minus x star dt. This is kind of trivial. If I integrate anything that doesn't have t, then this just comes outside and I'm left with the integral from 0 to 1 of dt, which is just 1. So in other words, I've just multiplied twice by another name for 1, and I have this, but this allows me to group it very nicely into what I have, and critically you'll see that we're going to get a difference of Hessians. Why do we care about a difference of Hessians? Let's flip back for a second and remind ourselves what are the main assumptions. You see here, this is our key assumption is Lipschitzness of the Hessian. And in order to use this, I need somewhere an expression that has the Hessian evaluated at one point minus the Hessian evaluated at another point. And that's exactly what we're doing here. Okay, so using this different name for 1 to write xk minus x star, I can write all of this expression. I can write xk plus 1 minus x star as the Hessian at xk inverse times the integral from 0 to 1 of the Hessian of f of xk minus the Hessian of f of x star plus t times xk minus x star, all of this times xk minus x star dt. You see how we did that? Okay, so now let's take a norm on both sides. And I'm going to use two facts. So first, recall that if I have any two matrices A and B, the norm of A times B is less than or equal to the norm of A and the norm of B. This is called the subadditivity, submultiplicative property. And also, if I have the norm of any integral, that's going to be less than or equal to the integral of the norm. And why is that? Just think of it with absolute value. It makes it more clear. If I have the absolute value of an integral is just a sum, so the absolute value of a sum is certainly going to be less than or equal to the sum of the absolute values of the terms. Because if I'm taking the absolute value outside, there's always a possibility for some kind of cancellation. Okay, so applying these two to this equation that I have here, I conclude that the norm of xk plus 1 minus x star is less than or equal to the norm of this whole thing. I'm going to use the first property and break off the norm of the Hessian, the inverse Hessian, times, let me delete this stray mark here, times the integral of the norm. That's the norm of the Hessian minus the norm of the Hessian evaluated at x star plus t times xk minus x star dt times the norm of xk minus x star. Now, finally, we're in place to use our Lipschitz assumption, because here I have exactly what we need. It's the norm of a Hessian evaluated at xk minus the Hessian evaluated at x star plus t times xk minus x star. And therefore, this term is upper bounded by L times the difference of what's inside. And writing out what's inside, you'll see that we've got xk minus txk and x star minus tx star, if I just take the difference of what's inside. So in other words, I have what's the difference between xk and x star plus t xk minus x star is just 1 minus t times xk minus x star. So this whole thing is now upper bounded by the Hessian, the norm of the Hessian inverse, times the integral of 0 to 1 of L times 1 minus t times xk minus x star dt times xk minus x star. I'm going to copy this onto the next page, and we'll continue from there. We've got a few more steps to go, but you can see we're getting quite close to what we need. Okay, so just copying from the previous slide, so far we have obtained that xk plus 1 minus x star is less than or equal to the Hessian at xk inverse, the norm of that, times the integral from 0 to 1 of L times 1 minus t dt times xk minus x star squared. And you can see we're getting quite close. Remember that the overall theorem promises me that xk minus x star is upper bounded by some constant, in particular L over m, times xk minus x star squared. And as we saw in the previous lecture, it is the power of that square on the right-hand side that gets me this quadratic convergence. Okay, so this term is pretty easy. This is just L times the integral from 0 to 1 of 1 minus t, so let's do that. This is the integral from 0 to 1 of 1 minus t dt, and just doing that, you'll see that this is equal to 1/2. So this is equal to L times 1 over 2. Okay, now let's think about how we can bound this term. And again, we're able to bound this by strong convexity. So remember what we said. First of all, this operator norm of a matrix that is positive semi-definite, in other words, all of its eigenvalues are greater than or equal to 0. Let me write this in a different color just to keep it a little bit cleaner here. If A is positive semi-definite, then this operator norm of A is equal to just the largest eigenvalue of A. And if A is positive definite and therefore its inverse exists, what is the largest eigenvalue of the inverse? It is 1 over the smallest eigenvalue of A. So if A is positive definite, then the norm of the inverse is the largest eigenvalue of A inverse, which is exactly equal to 1 over the smallest eigenvalue of A. How is this useful for us? It's useful exactly because strong convexity gives us a lower bound on the smallest eigenvalue of the Hessian of f of x. So f, little m strongly convex, tells us that lambda min of the Hessian is always greater than m over 2, which then therefore means that lambda max of the inverse of the Hessian is upper bounded by 1 over m over 2, or just 2 divided by m. So plugging in all of these bounds, I find switching back to our main color, that xk plus 1 minus x star is less than or equal to 2 over m, that's the bound of the inverse Hessian, times L times 1 over 2, that's the bound of the integral of L times 1 minus t dt, times xk minus x star squared. And this was exactly our guarantee. So let's just make a few points about Newton's method now that we've finished off with this proof. So we've seen a few things here. First of all, Newton's method has much faster convergence, but it requires more assumptions. What did we need? Well, compared to gradient descent, first of all, we needed that second derivatives exist. We don't even need to even know that a function is twice differentiable in order to run gradient descent and get linear convergence. We just need that the gradients are smooth, are Lipschitz, and that the function is strongly convex. So more assumptions, meaning in addition to strong convexity, in addition to smoothness, we also require that f is twice differentiable and that the Hessian is Lipschitz. So basically, if this doesn't apply, if you don't have a Hessian, you can't use Newton's method. We also saw that we require potentially much more computation. I need to compute the inverse of a dimension by dimension matrix. For n dimensions, we need to compute the inverse of an n by n matrix, which is about an n cubed operation. Of course, we also need to compute the product of that inverse with the vector, which is also expensive. It's a roughly n squared calculation, but I'm just going to stop at talking about the inverse because that dominates the computation. On the other hand, if I have these more assumptions and I'm willing to pay more computation, the payoff is potentially dramatic. So we have very fast, namely quadratic convergence. And to remind you, that means that I need order log 1 over epsilon iterations of Newton's method once I'm in the quadratic phase in order to get error epsilon. Or another way to say this is that the error scales like, again, it doesn't have to be 1/2, it could be some other constant, 1/2 to the 2 to the number of iterations. We saw that this is what quadratic convergence means compared to linear convergence, wherein the error scales like 1/2 raised to the t. On the other hand, this requirement of more computation is significant. So in our next series, we're going to talk about efficient or more efficient attempts to do things that approximate Newton's method. These are called quasi-Newton methods. We're going to pick this up next time.